In this EzEd video lecture, we are going to learn about friction, wherein we will take a look at wedge friction and ladder friction. Hey, it's time to concentrate now. Let us first take a look at friction in wedges. But before that, we should know what a wedge is. A wedge is a piece of wood, metal, or some other material having one thick end and tapering to a thin edge that is used to lift or shift heavy blocks, machinery, etc. Consider the diagram shown alongside. Here, two wedges are used in combination to cause a small horizontal movement to the heavy block of weight W. Force is applied to wedge N, pushing it down, thereby causing horizontal movement of the heavy block. In this case, two wedges are used to imparting a small vertical movement to heavy machinery of weight W. Force is applied to the wedge N, which is driven inside, causing vertical movement of weight W. The following steps are used to analyze wedge friction. Isolate the wedges and draw their free body diagrams, highlighting all the normal reactions and frictional forces between surfaces in contact. Since the dimensions are neglected, wedges are treated as particles forming a concurrent force system. Hence, only two conditions of equilibrium are used. The following problems will be helpful to understand the concept behind frictional force in wedges. The way we draw the free body diagram of a wedge show the normal reaction offered by the supports, compute the frictional force, and finally apply COE to the system to calculate the unknowns. Consider the following problem. Figure shows a block of 5,000 newtons kept on a horizontal surface. Two wedges of 6 degrees are used to push the block to the right. Find the minimum force P required to push the block. Coefficient of friction for all surfaces is 0.4. In this case, two wedges are used in combination to cause a small horizontal movement to the heavy block of weight 5,000 Newton. Force is applied to wedge A, pushing it down, thereby causing horizontal movement of the heavy block towards the right. We will now isolate the wedges and the block. The free body diagrams of the block and the wedge A are drawn. Now, we will apply conditions of equilibrium to the block. We will first equate the summation of all forces in the x direction to 0. Thus, we will be able to find an equation which gives us a relation between the normal reaction offered by the ground and the normal reaction offered by the wedge A. Thus, we equate the summation of all forces in the y direction to 0. Thus, we find the magnitude of normal reaction offered by the wedge should be equal to 2380.95 newtons. Next, we will apply conditions of equilibrium to the wedge A. We will first equate the summation of all forces in the x direction to 0. Thus, we will be able to find the magnitude of normal reaction between the wedges should be equal to 2499.13 newtons. Then, we equate the summation of all forces in the y direction to 0. On simplifying, we find the minimum force P should be equal to 2207 to just push the block. Let us now consider this problem. Two wedges B and C are used to raise a load of 50 kilonewtons resting on A. This is done by applying a horizontal force P on both B and C, as shown in the figure. Calculate minimum value of P required. Assume symmetry of loading. Slope of both wedges is 1:10. Coefficient of friction between wedge and ground is 0.3 and coefficient of friction between wedges and A is 0.15. In this case, two wedges are used to imparting a vertical movement to load of weight 50 kilonewtons on block A. Equal force is applied to both the wedges B and C, which is driven inside, causing vertical movement. We will first calculate the angle of the wedge using the slope given. This angle is calculated to be 5.71 degrees. We will first draw the free body diagram of the entire system. Because of symmetry of loading, the normal reaction offered by the ground on both wedges is the same. Now, we will apply conditions of equilibrium to the entire system. We will equate the summation of all forces in the y direction to 0. Thus, we will be able to find the normal reaction offered by the ground on both wedges is equal to 25 kilonewtons. We will now isolate wedge B and draw its FBD as shown. Now, we will apply conditions of equilibrium to wedge B. We will first equate the summation of all forces in the y direction to 0. Thus, we will be able to find the normal reaction between the wedge B and the block A is equal to 25.51 kilonewtons. Then, we equate the summation of all forces in the x direction to 0. Thus, we find that minimum value of applied force P should be equal to 12.6 kilonewtons to just raise the block. Hey, it's time to concentrate now. Let us now take a look at friction in ladders. All of us have used ladders at one time or the other to reach for things kept high. But every time while climbing the ladder, we are afraid that the ladder might slip. What we don't consider is the friction force at the wall and at the floor, which is responsible for preventing the slip. If these surfaces do not produce enough friction force, the ladder will slip. The mechanics dealing with friction in ladders, that is ladder friction, will be analyzed in this section. The forces acting on the ladder are the normal reactions and friction force at the wall and the floor contact points. The weight of the ladder, the weight of the person climbing on the ladder, and any other applied force. These forces together form a non-concurrent force system. Therefore, all the three conditions of equilibrium will be used to analyze the equilibrium of a ladder. The following problems will be helpful to understand the concept behind frictional force in ladders. The way we draw the free body diagram of a ladder, show the normal reaction offered by the wall and the floor, compute the frictional force, and finally apply COE to the system to calculate the unknowns. Consider the following problem. A man weighing 750 newtons rests a ladder against a vertical wall, making an angle of 30 degrees with the wall. The ladder is 10 meters in length and its weight is 1000 newtons. How high will the man be able to go before the ladder slips? Coefficient of friction between wall and ladder is 0.35. Coefficient of friction between ground and ladder is 0.2. In this case, a man weighing 750 Newton is trying to climb a ladder. We have to find how high he will be able to climb before the ladder slips. The forces acting on the ladder are the normal reactions and friction force at the wall and the floor contact points. The weight of the ladder and the weight of the person climbing the ladder. These forces together form a non-concurrent force system. Let the man climb a distance x on the ladder before it is on the verge of slipping. Let us first draw the FBD of the ladder, KL, resting against the wall and the floor. The weight of the ladder acts through its center of gravity, that is, at the center of its length. Now, we will apply conditions of equilibrium to the ladder. We will first equate the summation of all forces in the x direction to 0. Thus, we will be able to find an equation which gives us a relation between the normal reaction offered by the wall and the normal reaction offered by the ground. Then, we equate the summation of all forces in the y direction to 0. Thus, we find the magnitude of normal reaction offered by the ground should be equal to 1635.5 newtons. Substituting this value in equation 1, we find normal reaction offered by the wall to be equal to 327.1 newtons. Next, we will equate the summation of moments of all forces about point L to 0. On simplifying and then substituting the values of both the normal reactions we find the distance the man can climb before the ladder slips to be 2.4 meters. Let us now consider this problem. As shown in the figure, a 7-meter long weightless ladder rests against a smooth wall at A and a rough horizontal floor at B. An additional weight of 300 newtons is acting on the ladder and is concentrated at a distance of 3 meters from the bottom. Coefficient of friction between ladder and floor is 0.3. Can the ladder stand in a 60-degree position as shown? In this case, we have to find whether the ladder will stay in a state of equilibrium at 60 degree or will it slip. The state of the ladder is unknown in this case. Hence, we cannot take the friction force as. Let F needed be the friction force needed at the ground to prevent the ladder from slipping. Since the wall at A is a smooth surface, it will only offer a reaction force and there won't be any frictional force. Hence, the forces acting on the ladder are the normal reaction and friction force at the floor contact point, the weight of the ladder and the normal reaction force at the wall. These forces together form a non-concurrent force system. We will now draw the free body diagram of the ladder. Now, we will apply conditions of equilibrium to the ladder. We will first equate the summation of all forces in the x direction to 0. Thus, we will be able to find an equation which gives us a relation between frictional force at the ground and the normal reaction offered by the wall. Then, we equate the summation of all forces in the y direction to 0. Thus, we find that the magnitude of normal reaction offered by the ground should be equal to 300 newtons. Next, we will equate the summation of moments about point B to 0. On simplifying, we find the normal reaction offered by the wall to be equal to 74.23 newtons. Substituting this value in the above relation, we find the friction force at the ground, that is, the friction force needed at the ground to prevent the ladder from slipping to be equal to 74.23 newtons. Now, we will calculate the maximum force that the ground can produce, which is the maximum static friction force. Thus, the maximum friction force available is found to be 90 newtons. Since friction force needed is less than the friction force available, the ladder is in a state of equilibrium and will stand in the 60-degree position. Let's have a quick review of what we've studied in this lecture. A wedge is a piece of wood, metal, or some other material having one thick end and tapering to a thin edge that is used to lift or shift heavy blocks, machinery, etc. Usually 2 or more wedges are used in combination. We learnt that wedges are used to impart horizontal or vertical displacement to other blocks. Then, we learnt the steps involved in analysis of friction in wedges. These 2 steps must be implemented very carefully to correctly analyze wedge friction. Next, we learned about ladder friction. Then, we learned about the forces acting on the ladder, that is, the normal reactions and friction force at the wall and the floor contact points, the weight of the ladder, the weight of the person climbing on the ladder, and any other applied force. Then, we learned the steps involved in analysis of friction in ladders. These steps must be implemented very carefully to correctly analyze ladder friction. In this EzEd video lecture, we are going to learn about friction, wherein we will take a look at rope friction and tipping in friction. Rope friction is a term describing the friction forces between a rope and a drum, such as a flat belt wrapped around a rough pulley. Friction in both the cases of flat belt and a rope around a drum is considered to be the same, as the surfaces causing friction are in contact from only one side. Consider a lady is trying to fetch water from a well with the help of a rope and a drum. When one end of the rope is being pulled, only part of this force is transmitted to the other end due to the friction force. Consider the load in the bucket to be equal to W and the force applied at the other end to be P. Now let's analyze the first case. Here, the drum is smooth, hence there is no friction. We have to determine the force P to maintain equilibrium of the system. This will be equal to load W. In the second case, load W has to be lifted and the friction is not neglected. In this case, since the motion of the load is impending upwards, the frictional force will act all along the contact surface in the opposite direction. Hence, the applied force P will have to overcome both the load W and the frictional force F for impending motion. The applied force P is therefore greater than W. In the third case, the applied force P has to prevent the load from slipping down the plane when friction is not neglected. In this case, since the motion of the load is impending downwards, the frictional force will act in the opposite direction. Hence, the frictional force F helps applied force P in preventing the load W from slipping. The applied force P is therefore less than W. Hence, we can conclude that in rope friction, tensions are different on both the ends of the rope. On one side, the tension is more, known as tight side, T2, and on the other side, the tension is less, known as slack side, T1.
Seriously, pay attention. This is important.
Now, we will derive the relation between the tight side and slack side of a rope wrapped around a drum. Consider a rope wrapped around a rough drum. Let T2 and T1 be the tension on the tight side and the slack side respectively. Let beta be the angle of lap of the rope on the drum. The angle of lap is the angle made by the first and the last contact points of the rope and the drum with the center of the drum. The tension on the slack side T1 increases along the surface of contact due to frictional force. Consider an element of the rope subtending an angle d theta at the center. Let T be the tension on one face of the element, which increases marginally to T plus dt on the other face. Let N be the normal reaction offered by the drum surface and mu N be the maximum frictional force developed. Now, applying conditions of equilibrium to the rope element, first, we will equate the summation of all forces in the x direction to 0. On simplification, we will find that dt cos d theta by 2 minus mu n is 0. But for small values of d theta, cos d theta by 2 is approximately equal to 1. Hence, dt is equal to mu n. Next, we will equate the summation of all forces in the y direction to 0. On further simplifying and also neglecting the product of two small quantities, we find that n is equal to td theta. Substituting this value of n in above relation, we get dt upon t is equal to nu d theta. Since the tension increases from T1 to T2, as the angle of lap increases from 0 to beta, we will integrate the above equation along the same limits. On solving the above integral, we get natural log of t in the limits T1 to T2 is equal to mu theta in the limits 0 to beta. On further simplifying, we get this is an important equation which gives us the relations between tension on the tight side and the slack side of a rope. Remember that angle beta is in radians, not in degrees. Now, we will learn to solve problems on rope friction. The following problems will be helpful to understand the idea behind rope friction, the way we find the tensions on the tight side and slack side, and finally calculate the unknowns. Consider the following problem. A hawser thrown from a ship to a pier is wrapped around 3 full rounds around a capstan. The tension in the hawser is 6,000 newtons. A dock worker prevents the hawser from slipping by exerting a force of 100 newtons on its free end. Determine the coefficient of friction between the hawser and the capstan. In this problem, we know the tensions of the tight side and slack side. The angle of lap is equal 3 times 2 pi, as the hawser is wrapped 3 times around the capstan. That is, the angle of lap is 6 pi radians. Now, we will use the relation between the tension on the tight side and the tension on the slack side. On further simplifying and then taking natural log on both sides, we find the coefficient of friction mu to be equal to 0.217. Let's consider this problem now. A rotating wheel is braked by a belt AB attached to the lever ABC hinged at B. The coefficient of friction between the belt and the wheel is 0.35. Find the braking moment M exerted by the vertical weight of 75 Newton. In this problem, we have to find the moment exerted by the weight W in order to stop the wheel. Let T1 and T2 be the tension on the two sides. We will first compute the angle of lap, beta, which is found to be 225 degrees, that is 3.927 radians. The coefficient of friction is given as 0.35. Using the relation between tension on the tight side and the slack side of a rope, the ratio of tension of the tight side to the slack side is calculated to be 3.95. Let us now isolate the pulley and the lever and then draw their free body diagrams as shown. Let us now consider conditions of equilibrium to the lever. We will equate the summation of moments of all forces about point B to 0. On simplifying, we will find the tension on the tight side is equal to 175 newtons. Next, we will consider the FBD of the pulley and taking moment about O. This is the actual applied moment and is equal to the braking moment. On simplifying and then substituting the above calculated ratio, we find braking moment to be 26.14 Newton meters.
Hey, it's time to concentrate now.
Tipping is a very important concept that we have seen one or more times in our life. Consider an empty cupboard. If a person tries to push the cupboard ahead, it is easier for him to apply a force at a lower position in comparison to a higher position. If he applies force at a higher position, the cupboard may tip, that is, it may tilt over instead of sliding ahead. This phenomenon of the tilting of the cupboard is called as tipping. Consider a cupboard of weight W kept on horizontal surface. Consider the following case. The cupboard is kept on a horizontal surface and no external force is acting on it. Thus, only two forces, the weight force W and the normal reaction N offered by the surface, are acting on the cupboard. Hence, the cupboard is in a state of equilibrium. Now, let a man try to push the cupboard with force P, applied from the left. The force is applied at a height of h. The frictional force generated to maintain equilibrium is equal in magnitude to the applied force P. Let us now consider the second case. The force P is applied at a smaller height, h. This will form a clockwise couple trying to tip the cupboard. The magnitude of the couple is P into h. In order to maintain a state of equilibrium, the system will try to counter this couple by shifting the normal reaction N, which is equal to weight W, towards the right. This shifting forms an anti-clockwise couple of magnitude W into D to balance the cupboard. For equilibrium to be maintained, both couples should be equal to each other. Let us now consider this case. If the height of the applied force is now increased, the couple generated by the applied force also increases, such that the normal reaction N further shifts to the right to increase the magnitude of the balancing couple. Let us now take a look at this final case. The force N cannot shift beyond corner A. At this stage, if the height of the applied force is further increased, tipping takes place. Therefore, at the verge of tipping, the normal reaction N is at the corner of which P is at the maximum height. To analyze such a non-concurrent force system, we can use all the three conditions of equilibrium. Now, we will learn to solve problems on tipping. The following problem will be helpful to understand the idea behind friction in tipping. Consider a cupboard of weight 1000 newtons is to be shifted to the right. Coefficient of friction between cupboard and the floor is 0.2. Calculate the force P required to move the cupboard and the largest allowable value of H if the cupboard is not to tip over. In this case, we have to find the minimum value of force P required to push the cupboard. Let us now draw the free body diagram of the entire system. We will now apply the conditions of equilibrium to the cupboard. We will first equate the summation of all forces in the y direction to 0. Thus, we will find the normal reaction N to be equal to 1000 newtons. Then, we equate the summation of all forces in the x direction to 0. Thus, we find that the minimum value of applied force P should be equal to 400 newtons to push the cupboard. The cupboard is on the verge of tipping when the applied force is at the maximum possible height, that is H max. The normal reaction shifts to the corner Z. We will now apply the conditions of equilibrium to the cupboard. We will equate the summation of moments of all forces about the point Z to 0. On simplifying, we will find the maximum possible height is equal to 1.25 meters. Let us have a quick review of what we have studied in this lecture. Rope friction is a term describing the friction forces between a rope and a drum. When one end of the rope is being pulled, only part of this force is transmitted to the other end due to the friction force. Tensions are different on both ends of the rope. On one side the tension is more, known as tight side, T2, and on the other side the tension is less, known as slack side, T1. Then, we derive the relation between the tight side and slack side of a rope wrapped around a drum. This is an important equation which gives us the relations between tension on the tight side and slack side of a rope. Then we learned about tipping. Tipping is a very important concept that we have seen one or more times in our life. It is easier for a person to push the cupboard by applying a force at a lower position in comparison to a higher position. If he applies force at a higher position, the cupboard may tip. That is, it may tilt over instead of sliding ahead. Such a system which is about to tip is considered as a non-concurrent force system, and hence all the conditions of equilibrium can be used.